All right, although we do have something called the product rule for derivatives, unfortunately, there is nothing called the anti-product rule for integrals. It doesn't exist. It's a fake math kind of thing. All right, so there is nothing. Ooh, I don't like that. That I will have to do black. All right, so there is no anti-product rule. So in place of the anti-product rule, we need different techniques of integration. And so today, our technique is the U substitution technique for integration. So that's the rest of chapter 7, is all different techniques to integrate things. So today is U substitution, tomorrow will be trig substitution, we'll use integration by parts, we'll do tabular integration, all different techniques in order to integrate. All right, so start with something that you've seen as familiar, but it usually is when you have a product. So for example, our first integration is going to be of the product of x times the sine of x squared dx. The U substitution technique takes the interior of a nested function and replaces it with the variable u. And so as I look here, I look at the interior of that nested function and I see that as x squared. And so I'm going to assign u to replace x squared. But then I also have to replace the other parts. If I'm going to replace u with x squared, I have to replace the differential as well. So du dx would be 2x. And so then the differential, when I separate, would be 2x times dx. And then I separate that again so that I can have dx by itself, and I get du over 2x. So I make two substitutions in this equation. I am going to make the substitution for the interior. I'll make a substitution for x squared. I'm also going to make a substitution for dx. I don't have to worry about the x that's part of the product. That will take care of itself when I make my substitution. But there's always ever two. It's for what you chose for your u, and then it's what you're going to replace for your dx. So that will give me x sine u replacement, and then dx is getting replaced with the differential of du over 2x. And then we simplify. I didn't have to worry about the x that was out front, because what's going to happen to it? It reduces away. And so I can pull a 1/2 out to the front of my integral, and I'm left with the simple integral, the sine of u du. And so then I can integrate that to the negative 1/2 of the cosine of x, cosine of u plus c. And then my last step is to replace u with what it originally substituted for. So I have the negative 1/2 of the cosine of x squared plus c. And that is a quick and dirty u substitution. So it's just kind of an intro one. If things don't reduce away, what does that usually tell you? You picked the wrong u in the first place. Okay? So then go back and make sure that you've chosen the interior of the complex function. All right, so let's try another one. All right, this time let's integrate the product of the quantity 1 minus the cosine of t over 2, that quantity squared, and its product with, multiplied with, the sine of t over 2, and then that has dt on the end. So you have a couple different choices for your u at this point. but you want to choose the interior of the most complex. Okay, so you're not just going to pick t over 2. Although it is inside, that's inside cosine, which is after minus 1, which is also inside parentheses. So you want to pick something that's large enough. So my u choice right now is going to be 1 minus the cosine of t over 2. And choosing u well comes with experience. Most of you have a whole year's worth of experience on picking the right u. So you'll find you're choosing your u to be a lot easier. All right, our differential on u is going to be the positive sine of t over 2 times the chain rule of 1/2 dt. And then we want to separate the dt from the rest of it. So I'll end up with a numerator that has 2 du and a denominator that's the sine of t over 2. So that is what's going to be used in my u substitution. So my integral will simplify to the quantity of u squared, because that's what I chose my u to be, multiplied by the sine of t over 2, which I'm not going to worry about that right now, because I know that when I replace my dt with 2 du, it's also over the sine of t over 2, which will reduce away. What can I pull out to the front of this integral? The 2, the constant. So that'll leave me with the 2 times the integral of u squared du, and then that will simplify. So then we're looking at 2/3 of u cubed plus c. All right, so then we're left with 2/3 of the quantity now, 1 minus cosine of t over 2. That quantity now raised to the 3rd power plus c. Okay. All right, so last year that was day 1. On day 2, we introduced bounds. So we're going to do that all in the same day today. Great. All right. So now when we introduce bounds into the question, we've got 0 to 1/2 as our bounds. This is going to be 1 over the quantity, 2x plus 1 cubed. So we choose our u. What do you think would be a good choice here? All right, I agree. Okay, 2x plus 1. So then our differential is 2 dx. So we isolate dx, so we get du over 2. You also have a choice right now. You can either leave your bounds as is, do your u substitution, and then remember to change it back out of its u substitution at the end, and then you don't have to change the bounds at all. Or you could change the bounds right now and then never have to go back to x. You can stay in u the rest of the way. My advice is usually to change your bounds, because almost always the math on that is easier if you eliminate x altogether. So at this point you would change your bounds using the u substitution setup that you had. So using 2x plus 1 as your conversion, you'll convert your bounds. And so the new bounds will not be 0 to 1/2, but if I use 2x plus 1 to convert, what will the new bound be? 1. Okay, if I put 0 in, I get 1. Then if I put 1/2 at the top, I'm now going to get 2. And so then I'm looking at 1 over u cubed, and then the differential on that is du over 2. So I'm going to pull the 1/2 out to the front. I like to rewrite my u as u to the -3. I make less mistakes when I change it to a negative exponent. That's just me personally. If you don't have to do that, you don't need to, but I usually make fewer mistakes when I do. So then my new antiderivative is u to the negative 2 divided by the new power of negative 2 plus the constant that's going from bounds that are going from 1 to 2. Because I've changed my bounds, I don't have to change back to the variable x. I can stay in the variable u. So this would be negative 1 over 4u squared plus the constant c from 1 to 2. And I don't have to go back. So I can have negative 1 over 4 times 2 squared minus negative 1 over 4 times 1 squared. So I'm looking at negative 1/16 plus 1/4, which is 3/16 overall. So I'm not going to mark you wrong. If you don't ever change your bounds and you decide you want to go back to the x variable, that's fine. You just decide either way. Okay, last one. And then you can have a work day. All right, so our last one, we're going to integrate from the bounds of 0 to pi/4. And the product is going to be the tangent of x times the secant of x, quantity squared dx. Now here's where choosing your u might not always be exactly where I say it's always, like the interior of the most complex function. Because if you pick secant as your u, it will work eventually, but you might have to do a double u substitution later on down the road. Okay, it might be more advantageous for you to be able to see that right now this product is the product of a function and its own derivative. Okay, this is tangent times secant squared. Tangent and secant squared are derivatives. One is the derivative of the other, and so that might help you make your u choice. What would be the best one in this situation? Tan. And again, that comes from you having experience, knowing that du is the secant squared then of dx. So isolating, you'll end up with du over secant squared. And that just comes because you've had the experience of kind of being able to see down the road a little bit and predict what's going to happen. So then we want to convert our bounds. If u is chosen to be tan x, then our bound conversion will be going from 0 stays 0, because the tan of 0 is 1, but what will the upper bound now be? Careful. 1. Yeah, we just went through that. Yep. All right, so u is tan, so I've got u. Secant of x squared is still there, but my du got replaced to be du over secant squared of x. So really, this could not have been any cleaner. It works out to be u du. That's it. I mean, that's such a nice integral. So we're looking at 1/2 u squared plus the constant c from 0 to 1. So the answer is half.